Hello everyone, our lesson for today is about asymptotes. The objectives of this lesson is first to define an asymptote and explain its meaning in terms of the behavior of a function, to distinguish between the three types of asymptotes: vertical asymptote, horizontal asymptote, and oblique asymptote. Now to explain the link between limits and asymptotes, especially limits at infinity and limit at a point. Now, what is an asymptote? We draw an asymptote, but an asymptote, in fact, asymptotes are imaginary lines to which the total graph of a function or part of the graph is very close to, as you can see in the figure. This is the curve in blue. It's very close to the asymptote in red. So a curve approaches the asymptote, but it never touches. So the asymptote is a line for which the graph of a function converges. So it never touches the asymptote. The curve never touches the asymptote, but it approaches the asymptote. So the distance between the asymptote of a function and its graph is approximately 0 when either the value of x or y tends to plus or minus infinity. There are three types of asymptotes. First, the horizontal asymptote. Horizontal asymptote, as you can see in this figure, it's horizontal line, and hence its equation is of the form y equals k. So this is the horizontal asymptote. The second type is vertical asymptote. It's a vertical line. This is a vertical asymptote. Is a vertical line, and hence its equation is in the form of x equals to k. Now, oblique asymptote or slanting asymptote, it's an oblique line, so its equation is in the form y equals mx plus b. What is a vertical asymptote? A vertical asymptote is a vertical line of the form x equals k, like you see the line in red here. This is a vertical asymptote. So the form where f of x tends to plus infinity or f of x tends to minus infinity, they approach the line x equals k. If the graph approaches the line x equals k, then x equals k will be a vertical asymptote to the graph. So, in other words, if the limit of the function is equal to plus or minus infinity as x tends to k, then x equals k is a vertical asymptote. Now the function approaches the line when x gets close to k. So this happens when the function is very large, tends to plus infinity, or is very small, tends to negative infinity. Now how to find the vertical asymptote of a rational function? To find the vertical asymptote of a rational function, first, you simplify your function if it needs simplification. You simplify it to its lowest term. Then you set the denominator equal to 0 and solve for x. Let's interpret what we are saying by solving this example. So here, the function is already in its lowest term. Don't need simplification. We set the denominator 0. So x plus 1 is equal to 0, this implies that x equals to negative 1. Now you study the limit at minus 1 minus and minus 1 plus. At the point x equals minus 1. This is the way we study the limit. So you find the limit of f of x as x tends to negative 1 minus, it is 1 over minus 1 minus plus 1, so it is minus infinity. This is 0 minus. This is 1 over 0 minus, so it is minus infinity. Now, the limit of f of x as x tends to minus 1 plus means more than minus 1. 1 over minus 1 plus 1. So it is 1 over 0 plus, so it is plus infinity. This means that x equals negative 1 is a vertical asymptote for the graph. Look at the graph. This is the graph of 1 over x plus 1. X equals negative 1 is a vertical asymptote as x tends to minus 1 plus, so from the right side f of x tends to plus infinity. It approaches x equals minus 1 but does not touch it. As x tends to minus 1 or negative 1 minus f of x tends to negative infinity, approaching the asymptote but not touching it. Now, what is a horizontal asymptote? A horizontal asymptote is a horizontal line of the form y equals L. The function approaches y equals L when x tends to plus infinity or x tends to minus infinity. In other words, if the limit of f of x equals L as x tends to plus or minus infinity, then y equals L is a horizontal asymptote, as we can see in the figure. So here, as x tends to plus infinity, it approaches the horizontal asymptote. As x tends to minus infinity, also it approaches the horizontal asymptote without touching it. Now, methods to find the horizontal asymptote depends on the degree of the polynomial in the numerator and the degree of the polynomial in the denominator. We are talking here about rational function. So 1. If both polynomials have the same degree, we just divide the coefficients of the leading term. If the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote will be equal y equal to 0, which is the x-axis for sure. If the degree of the numerator is greater than the degree of the denominator, then you do not have a horizontal asymptote. You will have something called oblique asymptote. We will see it later. How to find horizontal asymptote of a rational function? Now, in this example, the degree of the numerator is 1. The leading coefficient is 3. The degree of the denominator is also 1. The leading coefficient is 1. So the horizontal asymptote will be equal to the ratio of the leading coefficient of the numerator, which is 3, divided by the leading coefficient of the denominator, which is 1. It's equal to 3. The horizontal asymptote here is y equals 3. In general, horizontal asymptote is the limit of f of x as x tends to plus or minus infinity. How you solve it? It is now the limit as x tends to plus or minus infinity of 3x plus 6 over x plus 1. You will be taking the monomial of highest degree, here you have x only, as a common factor. Then you divide by it. So 3x divided by x is 3 plus 6 over x. X as common factor, 1 plus 1 over x. Now, as x tends to infinity, you can eliminate x by x. 6 over x tends to 0. 1 over x tends to 0. So the limit will be equal to 3. So y equals to 3 is a horizontal asymptote. You can see the figure, how the curve approaches y equals 3 from the right and from the left. But now a small comparison between the horizontal asymptote and the vertical asymptote. Now the horizontal asymptote is of the form y equals k as x tends to plus or minus infinity. The vertical asymptote is of the form x equals k as y tends to infinity or y tends to minus infinity. We studied using the denominator, you put the denominator equal to 0. Now the horizontal asymptote may cross the curve sometimes, but the vertical asymptote will never cross the curve. Finally, we reach to an oblique asymptote. Now, an oblique asymptote is of the form y equals mx plus b. It's a straight line where m is not equal to 0. If m is 0, then it is y equal b, a horizontal asymptote. So it usually exists for rational functions, and mx plus b is the quotient obtained by dividing the numerator of the rational function by its denominator. So the whole numerator by denominator. This is an oblique asymptote. You see the function approaches the oblique asymptote, never touch it from left and from right. As its name suggests, a slant asymptote or an oblique asymptote is neither parallel to the x-axis nor parallel to the y-axis. So its slope is neither 0 nor undefined. So its equation is of the form y equals mx plus b, where m never 0. It's a real number. A rational function now has an oblique asymptote only when its numerator is exactly 1 more than its denominator in the degree. So the degree of the numerator will be exactly 1 more than the degree of the denominator, and hence a function with an oblique asymptote can never have a horizontal asymptote. So if the function has an oblique asymptote, it will never have a horizontal asymptote. Now, how to find an oblique asymptote? The first method is by using Euclidean division. You divide the numerator by the denominator, and the result is the oblique asymptote. So here the numerator is 3x cubed minus 1, denominator x squared plus 2x. We do Euclidean division to get 3x minus 6. So y equals 3x minus 6 is the oblique asymptote. Now we have another method. The second method, which we will use it always in the exercises to find the oblique asymptote, is by finding the limit of f of x over x as x tends to plus or minus infinity, because this limit will tell us whether the function or the graph behaves like a line or like a parabola or like a horizontal line. Case 1, if the limit of f of x over x is equal to a finite non-zero limit. This suggests that the function grows linearly. What do we mean by this? It has an oblique asymptote with slope a. Now to find the full asymptote, you find the limit of f of x minus ax. We will see this in a clear example. In this example, our main concern is to find the oblique asymptote, but before we start, let's write the domain of definition of this function. The domain of definition. Now, this function is defined everywhere except when x is 0. So x should not be equal to 0 because it is in the denominator. Then the domain of definition is negative infinity 0, union 0 plus infinity, which means that x equals 0 is a vertical asymptote. Okay. Now our main concern is to find the oblique asymptote. We have the numerator is a polynomial with degree greater than the denominator by 1. So the degree of the numerator is 2, the degree of the denominator is 1, which means that you have an oblique asymptote. So now the limit of f of x as x tends to minus infinity is the limit as x tends to minus infinity of x squared plus 3x plus 1 over x. How will we find the limit? We take the highest degree in the numerator and the highest degree in the denominator as common factors. So it is the limit as x tends to minus infinity of x squared into 1 plus 3 over x plus 1 over x squared. In the denominator you have x. Now, as x tends to negative infinity, 3 over x tends to 0. 1 over x squared tends to 0. You can eliminate x squared and x you can simplify. The result is the limit of x. It is the limit of x as x tends to negative infinity, so it is x. Similarly, you find the limit of f of x as x tends to plus infinity. It will be equal to plus infinity, which means that the curve or the graph admits f of x admits an oblique asymptote. Now, in order to find the oblique asymptote is in the form ax plus b. You need to find a and b. Now, what is a? A is the limit of f of x over x as x tends to plus or minus infinity in this case. So it is the limit of x squared plus 3x plus 1 over x squared, highest degree coefficient 1, highest degree coefficient 1, so it is 1. Sure limit as x tends to plus or minus infinity. Now, to find b, it's the limit of f of x minus ax. A here is 1, so it will be x minus x, f of x minus x, sorry, plus or minus infinity. So it is the limit of x squared plus 3x plus 1 over x minus x. Calculated, it will be the limit of 3x plus 1 over x as x tends to plus or minus infinity. It's equal to 3, which means that b is 3 and the horizontal asymptote is y equals x plus 3. Case 2, when the limit is 0, when the limit of f of x over x as x tends to plus or minus infinity 0, then this means that f of x grows slower than x. The graph will not have an oblique asymptote, but it will admit a horizontal asymptote. Let's see this example. Let's find the limit of f of x over x as x tends. So the limit of f of x over x as x tends to plus or minus infinity will be equal to the limit of, take common factor. First, this will be x cubed, x squared plus 3x plus 1 as x tends to plus or minus infinity. It is the limit minus infinity, x squared common factor, the highest degree monomial, 1 plus 3 over x plus 1 over x squared, denominator x power 3, tends to 0, tends to 0. You will have x in the denominator, so the result will be 1 over x, so the limit will be equal to 0. In this case, the function will admit a horizontal asymptote. In other words, when the degree of the numerator is equal to the degree of the denominator, the function admits a horizontal asymptote. Now, case 3, if the limit of f of x over x tends to plus or minus infinity, this means that the function grows faster than x. The graph will not admit an oblique asymptote this time, but it will admit a parabolic branch parallel to the y-axis. We will see how we'll find it in the example. Now, f of x equals x squared plus 1. The domain of definition of this function is R. There is no restriction on the domain, so it is minus infinity plus infinity. Now the limit of f of x as x tends to plus or minus infinity is always plus infinity. It is x squared. Now this function does not admit an oblique asymptote. So let's find the limit of f of x over x as x tends to plus or minus infinity. You will get the limit as x tends to plus or minus infinity of x squared plus 1 over x squared, which is over x, sorry, x squared plus 1 over x, which is the limit of x as x tends to plus or minus infinity, which is equal to plus or minus infinity. As x tends to plus infinity, f of x over x tends to plus infinity. Same for minus infinity, it tends to minus infinity. Then the function here has a parabolic branch parallel to the y-axis. As you can see in the figure, as x tends to plus infinity, the function has parabolic branch parallel to the y-axis. As x tends to minus infinity, the function has parabolic branch parallel to the y-axis.